This video is brought to you by the COSBI LAB Learning Center. Hello, my name is Angela Sanger, and I am the Applications Manager at COSBI. In this video, I will show you how to model interaction definition with COSBI LAB Model. In the How to Model Components video, using the EGFR network example, I demonstrated how to enter 3 components and a complex. In this video, I show you how to model interaction definition, the rules describing how components' state modify over time. Interactions are defined as dynamics in COSBI LAB terminology. The 4 types are global dynamics, to model the regulation of components; binding dynamics, to model association and dissociation of complexes; monomolecular dynamics, to model changes of active and inactive sites; and finally, bimolecular dynamics, to model enzymatic reactions. Before talking about dynamics, I will explain the concept of COSBI LAB model configurations. For example, we will model a simplified EGFR network with 3 sites. Now, all sites are in the state of free. If we want to add EGFR with all sites phosphorylated, we don't want to add a component, add all the sites again, and then put them in the phosphorylated active state. Instead, COSBI LAB Model allows us to create a copy of the component's structure by simply going to the Configurations tab. There, you can create a copy of the EGFR structure and then simply configure the sites. In the COSBI LAB Model terminology, we call these elements configurations of a component. When creating a component, COSBI LAB Model sets automatically a configuration with all sites set to free. In the EGFR model, we are not interested in the detailed production and regulation of EGF. However, we still want to account for the EGF abundances change. We model such modifications with global dynamics. Specifically, we want to include the synthesis of EGF. The synthesis of EGF is modeled through the synthesize command of global dynamics. The degradation of EGF is modeled through the degrade command of global dynamics. You notice that I wrote EGF_init. This is the default configuration of the EGF component. The global dynamic needs to know in what configuration the component can be added or removed. Also, you notice there is a column compartment, where system is entered as default. This column specifies in which compartment the dynamic is valid. For EGFR, we need 3 compartments: system, membrane, and cytosol. Compartments are defined in the Compartments tab. These compartments are nested. First, I add a membrane nested in system. Then, I add cytosol nested in membrane. Now let's go back and see the compartment structure represented in the global dynamics. There, we leave system selected for the EGF production and reduction. Next, binding dynamics specify complex formation and dissociation between components. Before we can enter the homodimerization, we need to have sites along which the binding can occur. Let's enter them now. Now we go to the tab called Binding Dynamics and enter association of the homodimer EGFR. This rule defines association and dissociation between EGFR. Currently, the binding will happen always. However, the correct behavior is that EGFR needs to be bound to EGF so that it can form homodimers. How do we model such a restriction? The binding dynamics let us set conditions. Before 2 EGFR can form homodimers, they need to first be bound to the ligand EGF. We express this by a condition, saying that the respective site for the ligand needs to be bound. For the homodimers, both conditions are identical. If we have mixed components, the conditions would be different. Looking at EGFR system, we see that the compartment where the homodimerization happens is membrane. Let's change this in the compartment column of the binding dynamic. Now, let's move on to monomolecular dynamics, which specify rules to change the state of a single component. We define them under the Components tab. In our simplified model, EGFR has only 3 sites that can be phosphorylated. Now, we model the phosphorylation of the first site via a monomolecular dynamic. First, we write what should happen, namely, the phosphorylation of this new site. Then we add this restriction. The monomolecular dynamic happens only when EGFR is in the dimer form. The dimer site must be bound. Looking at the overview of the EGFR network, we see that the sites are on the border of the membrane. Therefore, we need to specify that the monomolecular dynamic is active in the membrane. COSBI LAB Model uses a narrative language to define such actions and conditions. Now let's see how to model enzymatic reactions. In COSBI LAB terminology, they are called bimolecular dynamics. We first need to add a phosphorylation site to the SHC. Then we add a bimolecular dynamic that describes the phosphorylation of SHC. Here, the EGFR plays an active role and phosphorylates a passive component, the SHC. With biomolecular dynamics, we model such non-symmetrical dynamics. We need to add a restriction because EGFR can activate SHC only in dimer form and when one of its sites are phosphorylated. Also, we need to define that the interaction takes place across two compartments as EGFR is in membrane and SHC in cytosol. We express this in COSBI Lab model by adding the compartment name directly to the component. At this point, the qualitative part of the model is complete. To conclude, you've seen how to use global dynamics to model EGF regulation in system, binding dynamics to model the homodimerization of EGFR during the simulation, monomolecular dynamics to model sites change of EGFR from inactive to active, and finally, how to define an enzymatic reaction with SHC across two compartments using a biomolecular dynamic. This concludes the COSBI Lab How to Model Interaction Definition video. Please visit the Learning Center for more videos, including the next step in the modeling process, parameter quantification. Thank you.